Okay guys, so due to inclement weather we are forced to have some makeup classes in this way. I'm going to record a couple of clips, video clips, where I will present something that I was supposed to do in class. So let me first recapitulate what we have done so far. At least a couple of important things. First of all, we saw that if omega is the set of all outcomes in a certain experiment, then in general there might be subsets of omega whose probability we cannot assign, or to whom we cannot assign probability. We had an example of Vitali set when we had a uniform distribution on some interval. So the question is, what are, given the experiment, relatively general situation, in a relatively general situation, what are sets or subsets of omega, the set of all outcomes, whose probability we can compute, or actually to whom we can assign probability. So in general, that can't be always the power set of omega. Then we had, if you remember, that coin flipping example where we alternatively flip coins. I flip coin first. If it's heads, you play. If it's tails, I win. So if it's heads, you play, and if it turns tails, then you win. Or for otherwise, if it's heads, it's my turn again. And then we play alternatively until somebody gets tails, and that's where we stop. So it's quite a realistic example where question of asking what's the probability that I win involves the countable union of events that we saw last time. So if an is an event that we play exactly n times, then if you remember, probability that I win, so the event that I win is actually event which is a disjoint union of all odd ANs, okay? And you win is disjoint union of even stopping times. We immediately come across an example where we really need that if we can compute probability of AN, so if AN is in that domain, if you remember, by A we denoted the domain of probability, we want union, if they are disjoint, we want countable union also to be in A, alright? And we would also like to know if A and B are in the domain of the probability function. We would like to be able to compute probability that at least one of the events happens. So in other words, we would like A union B to be in A. We would also like A intersection with B to be in A, which means that we would like to be able to compute probability, or to assign probability to the event that both events A and B happened. Okay, what else? We would also like P of omega to have equal to 1. So in particular, we would like omega to be in the domain of P. Next, we would also like the empty set to be of probability 0. So in particular, that means that empty set is we would like to be in omega. And also A without B, if A and B are in A without B. We would also like to be able to compute that probability. There are almost any experiment, almost any experiment, you can come up with some reasonable or realistic examples of events A and B where all these requirements or all these questions, what's the probability of all these events, is really something that makes sense. So all these are requirements for our domain A of our probability. Okay, so we saw last time, or actually second to the last time, that all these can be compressed into just one. This one is bad. I'm going to take some other marker. Let me see this one. Oh, this one is even worse. Okay, let me grab some other marker. Alright, so after I erase the board, we continue. So all those requirements, all those things that we like our probability or set function that we call probability, all those things that we like it to satisfy, they can all be written. We had that 2 weeks ago, I believe, that all that is equal. All those requirements are equivalent with saying that omega is in the domain of probability domain. That if A is in A, then the complement is in A. So if we can compute probability of A, then we should be able to compute probability of A complement. But computing doesn't just mean that being able to calculate. It means that actually we can assign some probability, or in other words, that A complement is in the domain. And of course, we would assign 1 minus P of A. And the last requirement, if we have a sequence, infinite sequence of events or sets which are in the domain of function P, then the union of all those, so ANs are not necessarily countable, this countable union is also in A. So we can also compute the probability of this countable union. So that's what we had 2 weeks ago, and it's easy to see that if A is non-empty, that means there is at least one set A with in the domain of P. Then also a complement is in A by this requirement or this axiom, and so is the union. Simply take all these to be A1 to be A, and A2, A3, etc. to be a complement. So the union is just the same as A union A complement, which is the entire omega. So actually we can delete this requirement. So everything is compressed or contained, all those requirements that we had about union, intersection, difference of sets being in A and complement being in A, all that is contained in these two requirements, okay? As long as we assume that domain of P is non-empty, which of course otherwise would be trivial. There wouldn't make sense not to require that. All right. So P, the set function defined on some subsets of omega, and the collection of those subsets, which we call A. Probability is a set function defined on this A, so it's a collection of subsets of omega that map these to, let me say, 0 infinity, or although we can just say interval 0, 1. So it's a non-negative, so real valued non-negative set function defined on some collection of subsets of omega that satisfy this property. Okay, and what are the requirements for P? Well, that P of omega is 1, or let me write that as the last requirement. All that we want is that probability of this joint union of ANs, so if ANs are in A and they are disjoint, then probability of the disjoint union is the series and goes from 1 to infinity P of AN. And we had one such example. It's actually probability of I win, or probability that you win. Okay, and so that's one requirement. The other requirement is that P of omega is 1. Alright, that's what we had. Alright, so this domain of function P is called sigma algebra, as long as it satisfies these properties, and the P, the set function, non-negative real value set function defined on sigma algebra, is called probability if it satisfies these two requirements. So that's what we had recently, and there are also a couple other things that we discussed, which I would also like to mention here. So let me first erase the board. Okay, so we continue. We also had the uniform distribution on some interval. So if omega is some interval AB on the real line, what do we mean by uniform distribution? Well, probability of getting some number, of picking a number in some interval inside AB, inside omega, is actually equal to, so probability of some interval I, so I is the interval subset of omega, probability of I is actually length of I divided by length of omega of the entire, so B minus A. So this is fixed, so let me write length of I divided by B minus A. So the denominator is fixed, so we actually see that the probability of any interval in omega is proportional to its length. Okay, so that's how actually we define probability, uniform distribution. But now, can we define probability of some events which are not intervals? And we saw that we cannot do that. We had that Vitali example, Vitali set. But the question is, for what intervals I can we compute probability under uniform conditions, probability of that set? So we want to build, actually, starting from intervals AB, we want to build a sigma field which will be a domain of function of our set function P. To do that, we can first observe that finite union of disjoint intervals A1 through AN, A1 through AN, so if they are disjoint, then probability of that disjoint union, I goes from 1 to n, or let me say k goes from 1 to n, ik, should be the sum k goes from 1 to n p of ik. So now we have a set E called elementary set, which means it's a finite disjoint union of elements of intervals. Okay, so it's a disjoint finite. We take only finite unions, but disjoint. Ik. All right. So we can define probability of E. Simply, it's going to be the sum of P of ik's divided by B minus A. So the length of these ik's divided by B minus A. Okay. And we can also immediately allow countable disjoint union and say if a set is countable disjoint union of intervals, then the probability of that set is the series of probabilities of ik's. But each time you are using probability, you are computing probability, what you are actually doing is computing the length of the intervals divided by the length of omega. So actually probability P, when you deal with uniform distribution, is, you can think of it just as a scaling of length. So basically, when dealing with uniform distribution, if you want to extend the definition of uniform distribution to compute probability of larger, broader class of sets, not just intervals, then you basically need to define length to that for that broader class of sets. So basically our problem is, how do we define length if instead of intervals we have or instead of disjoint finite or countable union of intervals, if you have something larger. Well, and also we want that to that collection of those sets whose length we can compute, we also want it to be a sigma field for the reasons we mentioned earlier that we want our probability to have. Okay, so the question is, now we are in a search for sigma field that contains intervals, or let's say just contains these elementary sets. So elementary sets are finite disjoint unions of intervals. So if you have this collection of elementary sets, can you extend it to some sigma field? Of course, the answer is yes. And how can we do that? Well, and of course, not only that we want some sigma field that contains intervals and elementary sets, we also want the length to be naturally extended from usual definition of length as the difference of right endpoint minus left endpoint for intervals. So how can that naturally extend so that we still keep that property of sigma additivity. So sigma additivity is just that the length of countable disjoint union is the series of lengths of each term. Okay, so how do we do that? Well, we mentioned Carat-Theodori theorem, and we also mentioned claim that the collection of elementary sets is an algebra. So if E is a collection of elementary sets, then E is an algebra. What it means is just like sigma algebra, it's except that instead of it's closed under countable union, you just allow it to be closed under finite union. So basically, omega is in E, or actually we can even drop that because it is contained in the other two requirements. So if E is elementary set, so is its complement. In other words, if you can define, if E is a finite union of intervals, so is its complement. If you think about it, it's really easy to show that. So if you have, just let me give you an example. I'm not going to show you, just to illustrate. If our E is the union of these guys, then its complement is the union of these guys. So those are again intervals. So basically, it's quite simple. But we are not going to spend time on details. Okay, so that's one thing. And the other thing is that if you have two elementary sets, say E1 and E2, then its union is also elementary set. Is also elementary set. Again, if you have, so this is A, B, just to illustrate, if this is E1 and if, say, this and this is E2, then when you take a union of overlapping intervals, so union of intervals with non-empty intersection, are actually another interval. So if you take union of these two red intervals and this green one, what we get is this entire interval here. Okay, and so the union of E1 and E2, we see that it's again union of some intervals. So it's just an illustration to show that it should really be true, but we are not going to spend time on details. So it is algebra, but what it's not the sigma algebra. That's a problem, and I'm not going to show that. So now we have Carat-Theodori theorem, which says that if you have additive function, or actually, additive function, which we want to think of as a length. So, but any additive function, if you have an additive set function mu, on some algebra. So in other words, mu is a set function from E, some algebra. In this case, we will think of E as elementary sets. No negative. All right. And if mu of omega is finite, in our case it's actually 1. This is 1. Then, and if you have this joint union of elementary sets, so EK, or sets from this algebra E, k goes from 1 to n, then sum of k goes from 1 to n mu of ek. If that's true, so one requirement, other requirement, third requirement is that if A is A and as well as E1, E2, blah blah blah, countably many E's in E, such that A is subset of this union, which is not necessarily disjoint union, yeah. then mu of A is less than or equal to series k, n goes from 1 to infinity mu of an. All right, this property is called sigma subadditivity. So basically, if you have set A and if you have sets ENs which completely cover A, so that's what this requirement, then probability or length or in general measure of A should be less than or equal to the sum of all or series of all measures of these sets. So if all these are satisfied, then we can extend mu to be in a unique way to be a measure on the minimal sigma field that contains E. All right, so there is an extension mu, let me say mu bar, so let this denote minimum sigma field containing E. We'll talk about that. I'll show you that such sigma field does exist, so but for the moment just take it as granted. So we can extend mu on the minimum sigma field so that it agrees with mu on this algebra E. Okay, so that mu bar restricted on E is actually mu. Okay, in fact, Carathéodory theorem is more a bit more general. We assume here that mu of omega is finite. In fact, it suffices mu to be sigma finite, which actually means that you can partition omega as a countable disjoint union of sets whose all measures are finite. Okay, so for example, real numbers, mu of the length of the entire real line is infinity, but you can represent R, the real line, as the union of intervals from n to n plus 1, and the length of each of them is 1, but actually it just suffices to be finite. Okay, so that's more general than this situation, but this is fine with us. Okay, we can just talk about this. Okay, so that's Carathéodory theorem. So, in our case, when E is collection of all elementary sets, which is an algebra, we can extend it to the minimum sigma field containing this algebra E. So what is actually minimum sigma field containing this algebra? It's actually very easy to see that if you have two or more sigma fields, their intersection is also sigma field. It's really elementary exercise in set theory, just plus using a definition of a sigma field. So sigma of E. Define sigma of E as intersection of all sigma fields F, such that F is in the collection U, and U is the collection of all sigma fields, or sigma algebras, sigma fields F that contain this algebra E. Okay? So this collection U is non-empty because if you take P of E, the power set of E is a sigma algebra. Power set of any set is always sigma algebra on that set. So P of E is in this collection U. Definitely P of E contains E. Alright, so definitely U is non-empty. Alright, and we can even show that this is a sigma field. Why is it sigma field? Well, we just need to check those two requirements. Well, first of all, sigma of E is non-empty because E is contained in it, and E is non-empty. And so if we have the elementary set in, if you have, let's say, F in sigma of E, why is its complement also in sigma of E? Well, if F is in sigma of E, that means F belongs to this intersection, which means F, set F belongs to each of these sigma fields F. So for every F in this collection U, capital F belongs to the sigma field F. Alright? But if F belongs to F, that means that the complement is also in F, simply because F is a sigma field, so it's closed under complementation. Alright, but that's for every F in this family. Therefore, F complement belongs to the intersection of all F's when F runs over the collection U. So that's exactly sigma of E. So that means that means sigma of E is closed under taking complements. Now, why is it closed under countable union? Here is why. Again, elementary exercise. So suppose F1, F2, blah 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 is a sequence in sigma of E. Alright? And so for each n, since Fn is in here, then Fn is in this intersection, so Fn is in F for all F in U. Okay? So if that's true, because F is sigma field, and for every n, Fn belongs to F, union of Fn's is in F as well. And that's true for all F in U. So basically, since it's true for all F's, this countable union must belong to the intersection of all F's, which is, belongs to the intersection of all F's, which is actually sigma of E. So you see, we used property of sigma fields F being closed under countable union to show that sigma of E is also closed under countable union. And a couple of minutes ago we used the closureness under complementation of each sigma field F to show closureness under complementation of the sigma field sigma of E. That's quite a common way to use weapon that you have, or good things about some class. If it's true for each element of that class, that property will be inherited by intersection or sometimes union. It depends on what notions you are dealing with. Okay, so sigma of E, the intersection of all sigma fields containing E, is sigma field. Now, why is it? What do we mean by sigma of E being the smallest sigma field containing E? Well, definitely it contains E. We already established that. But what does it mean, the smallest? Well, the smallest in the sense of inclusion. In other words, if there is some other sigma field F containing E, we want to show that sigma of E is contained in that F. That's what we mean by sigma of E being the smallest sigma field containing E. Well, why is it so? Well, simply because, by definition, so let me call this F, say F star. F star. Okay, sigma of E is intersection of all F's from collection U, and U is collection of all sigma fields containing E. Alright? But since F star is a sigma field containing E by assumption, then F star is in U. So one of these F's is F star, and the intersection of all of those F's is definitely subset. This is definitely subset of just one of these, okay, in particular F star. Alright, so we see that sigma of E is subset of F star. Okay, so we showed that sigma of E is the smallest sigma field containing E, the smallest in the sense of inclusion. All right. Okay, let me erase this. Okay, so we showed that if E is a collection of elementary sets, algebra of elementary sets of some interval omega, then sigma of E is the minimal sigma field containing E, and this sigma of E is called Borel sigma algebra, of set or of interval omega. Now, if you, instead of omega, if you take R, you can take R as a disjoint union of intervals n plus 1, okay, and goes from 1 to infinity, and build this E for each n for this interval, so say En, then we will take collection E let me say ER to be collection of all sets E, which can be written as the union of ENs, where EN is elementary set in this nth interval. Okay, and basically, and then take the minimum sigma field containing this ER, and of course it's easy to see that ER is a sigma algebra, that it's an algebra, and sigma of ER, the minimum sigma field containing ER is called Borel sigma algebra on real in the real line. So sigma of ER is Borel sigma algebra, or sigma field. They are synonyms. We said that. Borel sigma algebra in R. Now, there is nothing special about real lines. We would also like to talk about uniform distribution in plane. All right. So instead of elementary sets being disjoint union of intervals, we can take elementary sets in the plane being disjoint unions of rectangles. So rectangles are some sort of two-dimensional intervals, and we build algebra of elementary sets through those rectangles, and then build the minimum sigma field containing those elementary sets. Okay, and also in 3D, 3D versions of intervals, or we can just call them 3D intervals, are actually parallelepipeds, and elementary sets in 3D are actually finite disjoint unions or finite unions of elementary. We can actually just set finite unions, not necessarily, we don't need to say disjoint. Finite unions of parallelepipeds, so 3D intervals. Or in general, if you have RD, so d-dimensional vector space RD, we can build elementary sets which are finite unions of d-dimensional intervals. So what would be d-dimensional interval? Well, it would look like remember that notation, angular parentheses, A1 B1 cross A2 B2 cross blah blah blah, AD BD, okay, where this left angular parenthesis can be either open or closed, so either include this point or not, or exclude or include, and this one stands for either this one or this one. So you can take here open and here closed, and here closed or open, whatever, whichever combination you want, and also on the right hand side as well. So those are d-dimensional intervals, and finite unions of them are elementary sets in RD, and you build sigma of that algebra of elementary sets, and that's what Borel sigma field in RD is. All right. So very often Borel sigma field in RD is denoted by B of RD. In the book, the red denotes, in our textbook, the red denotes this Borel sigma field by script r to the d. Okay, so this is not a collection of vectors in d-dimensional vector space. It's actually a sigma field. Okay, so that's pretty much all what we had so far in a nutshell. All that we have done so far in those 3 weeks when we did have classes. Alright, so just like we generalized definition of length for intervals for elements of sigma algebra, Borel sigma algebra sigma v, or I can just call it B of R, Borel sigma algebra in a real line. We in 2D sigma of E, the corresponding, or B of R squared, the corresponding B of R squared would be a generalization of definition of area. So you start with rectangles and then finite disjoint unions of rectangles, and then build a sigma algebra that contains those elementary sets. Okay, so in 2D we can in that way generalize notion of area, and in 3D in the same fashion, or actually this is this all work done can be repeated with almost verbatim, can be repeated for 3D or in general d-dimensional case. Okay. All right. So what else do we have? Now the question is, are we happy? Or now we have defined length, not just for intervals, not just for finite unions of intervals, not just for countable unions of intervals, but actually for all sets in B of R, or in B of R squared, or in B of R cubed. So are we happy with that? Or can we stop, or do we have to continue enlarging sigma field and getting some larger sigma field? Well, it turns out in some situations this might not be satisfactory. But before we see that, I would like to go back to general case when you have a measure on some sigma algebra. And that's something that I should have talked about a bit earlier. Let me find it. Okay, so here is the theorem. It's in the textbook. It's theorem 111, and it's actually on the second page of our textbook. So it says that if you have a measurable space, omega f, so that means omega is some set and f is a sigma field on omega, which means some collection of subsets of omega, which makes a sigma field. And if mu, so this is a measurable space, and if mu is a measure on this space, so when you add measure, then it's called measure space. Measure space, not measured. Maybe saying measured space would be more appropriate, but That's the definition. It's called a measure space. All right. So if you have a measure space, then a couple of basic properties of measure: monotonicity. Monotonicity says that if A is subset of B, then mu of A is less than or equal to mu of B. Why is it so? Well, if A is subset of B, we have a picture like this. Alright? So you can decompose B as a disjoint union of set A and this remainder, which is actually B minus A. So B is a disjoint union of A and B minus A. Now we don't worry whether we can compute measure of B minus A, because since we of course assume here that A and B are in F. All right, so we know what mu of A is. It is defined, and mu of B is also defined. And so since F is a sigma field, B minus A is also in F, which means mu of B minus A is also defined. And now by additivity of measure mu, we have mu of B is mu of A plus mu of B minus A. Alright? But this is non-negative, this is greater than or equal to 0, so this sum is definitely greater than or equal to just this term. So we have that mu of A is less than or equal to mu of B. So that was easy. That was easy. Alright, next property is that subadditivity. So subadditivity so in the definition of measure, we just say that measure of the countable disjoint union is the series of measures of each component in that union. But subadditivity says that if A, A1, A2, blah 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 are in sigma field F, which is the domain of mu, and if A is subset of this countable union, in other words, if ANs cover A, then mu of A is less than or equal to the series and goes from 1 to infinity mu of AN. Alright? This can easily be shown by, again, a similar trick that we have seen already. So if you have A, and if ANs cover A, so we have some situation like this, alright? You can start with, so if this is A1, then we will, the idea is to write A as disjoint union of what, so now disjoint union of what intervals, of what sets. Well, those sets are going to be defined using ANs. So if this is A, then A1 intersected with A, that's going to be our A1 prime. So A1 prime is A1 intersected with A. Now we want to add the contribution of A2 in the covering of A. So it's going to be not the entire intersection of A2 with A, but just that part which is not already contained in this previous set. So basically A2 prime, is going to be defined as A2 intersected with A, but then we take out A1 prime. And in general, AN prime is when you take AN intersected with A and then subtract all previous contributions from previous AK. So basically union of AK prime, K goes from 1 to n minus 1. Okay, now it's easy to see that A is countable disjoint union of these AN primes, and goes from 1 to infinity, so it's a disjoint union. It's really easy to see, and so we can now use additivity, which is the property of measure by its definition. So we have that mu of A is mu of this, but by sigma additivity, this is, so mu of A, which is this, is equal to, by sigma additivity of measure mu, series n goes from 1 to infinity, mu of AN prime. Okay, and now each AN prime is when you take AN and intersect it with A. So this set, this intersection of AN and A, is definitely less than AN, I mean contained in AN. And when you subtract something more, then it's even less than that. So definitely this set is a subset of AN. So by this previous property, mu of AN prime is less than or equal to mu of AN, because AN prime is subset of AN. So this is less than or equal to, now this is true for every n, so mu of AN, and that shows this property. Okay, now another property of measure mu is continuity from below. Continuity from below. Number 3. From below. What's continuity from below? Well, if you have sets A, A1, A2, blah 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 in F, and this sequence of ANs is increasing, so that the union of all of them is all of A. So in other words, if we have AN subset of AN plus 1 for every n, and if the union of all these ANs is the entire A, then mu of A is simply the limit of mu of AN when n goes to infinity. Okay? So why is it called continuity from below? Well, first of all, why continuity? Because it looks like you pass limit under the mu. Okay, but why from below? Well, the picture tells thousand words. So if this is A1 and then A2 and then A3, blah blah blah, so you have increasing sequence. So each time you add some new set, you get larger, but increasing. I mean, each set contains all previous, and finally the entire union of all these is A. So basically this is definitely increasing sequence, so it goes from below, so it rises all the way up to this, so that's why it's continuity from below. Okay, so you are taking ANs larger and larger, and mu of AN is getting larger and larger. Okay, all right, so why is this true? Well, again, similar trick as in the previous property. So basically you take this union of ANs and decompose it into disjoint countable union. So take that disjoint countable union to be a set of BNs. So B1 is A1 and B2 is going to be the contribution of the next term. Alright, so B2 is just A2 minus A1. Alright, so now B3 is going to be contribution of the third set, A3, so without contributions of the previous set. So B3 is going to be A3 minus the union of A1 and A2. And in general, Bn is AN minus, so the contribution of AN minus the contribution of previous A's. So that means union K goes from 1 to N minus 1, AK. Alright? And obviously, I mean, it's really easy to show that that actually for every N, AN is the disjoint union of BK's. K goes from 1 to N. So for example, just look at the union of first three B's. So B1 union B2 union B3. So it's this A1 union this set union this set. Well, it's the same thing as A3, and that's actually true for every N. So so we have this, and also the union of ANs is actually the disjoint union of BNs. So now this is a countable disjoint union, but this is A. So mu of A is mu of this. So by sigma additivity of measure mu, this is the series and goes from 1 to infinity mu of Bn. And now this is, now we can just write this definition of the series. So this is series, but what's the definition of series? It's a limit of partial sums. So this is a limit when n goes to infinity of the nth partial sum. So this is series, so nth partial sum is series, k goes from 1 to n mu of bk. Alright? But because what now? Yes, these guys, because Bn is are disjoint, this is a limit, we just copy limit, but this is just mu of union, disjoint union, k goes from 1 to n of bk's, alright? But now, alright, is this visible? Yes, okay. But now, I'll have to change marker, okay? So now, this guy here, so this is just finite additivity of measure mu, so which is a immediate consequence of sigma additivity of measure mu. So now this thing, because of this, is just mu of an. So we are basically done. So now this is the limit of, when n goes to infinity, of mu of an. So we are done. And so much about continuity from below. We will be using it frequently. Next is continuity from above. What's continuity from above? Well, okay. What's continuity from above? Continuity from above. Continuity from above is the following. Instead of having increasing sequence, now you have decreasing sequence, and you are taking their intersection. So suppose A, A1, A2, blah blah blah, are in the sigma field F, which is the domain of our measure mu, and what? And suppose that we have that this is decreasing sequence. So A n plus 1 is contained in n for every n. All right? And suppose that A is the intersection of all these. Well, then mu of A is the limit of mu of ANs when n goes to infinity. Okay? Why is it so? Again, picture helps a lot. Alright, so we have A1 and then A2 and then A3, blah blah blah, and this thing here is intersection of all these. So we have dot 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 because there are infinitely many of that. Okay, so well, it's really easy to show just using continuity from below, because you can now reverse the order. Instead of having ANs, take their complements. So you have A1 complement is this guy, so this is omega. A1 complement is this thing here. Now A2 complement is all that, but then including also this part. So if you define Bn to be An complement, you have that Bn is increasing sequence, and so you use continuity from below, which you just showed, to show that limit of Bn is equal to the union of all Bn's, but by De Morgan's laws, the union of all Bn's are An complements. The union of all An complements is actually the complement of the intersection of An's, and you will show, so you can just fill in the details to show that this is true. Okay, so those are properties of measure, and in particular, remember the difference between measure and probability is just that for probability we require that it's a finite measure, so that probability of the entire omega is 1, okay? But if you you still have sigma additivity as a key property of measure. That's all what we require about measure, and that it's non-negative for every set in the sigma field. So basically, yeah, this all holds for any probability, because this holds for. Oh, there was one thing I should have said here. At least one of these guys, an has finite measure. So mu, I forgot to say that mu of an 0 is finite for some n 0. That's extra condition that we don't have in, there is no some corresponding condition in this continuity from below. So when you have continuity from above, you have this extra condition that at least one of them is finite. And then you will have that. It's easy to construct counter example. You can take real line, and you can take an to be interval from n to infinity. Now clearly, clearly this is decreasing sequence, and this sequence converges to empty set. So the intersection of all an's is the empty set. But mu of an obviously is infinity, the length of this interval. So the limit of mu of an is infinity. But on the other hand, A itself is an empty set. The intersection is the empty set. So mu of empty set is 0. So that's a counterexample of this continuity, this property continuity from above, if you don't assume that for at least one index or for at least one set in this decreasing sequence, you have finite measure. Okay, all these have infinite measure. That's the problem. Okay. So much about that property, and now back to Borel sigma fields. Okay, so back to Borel sigma fields. If B of R D is Borel sigma field in D-dimensional case, the question is, how large is it? So are we happy with just being able to define measure or volume, d-dimensional volume for sets which are just in this minimum sigma field containing corresponding elementary sets? Well, it turns out that the cardinality of this for any given dimension d is always cardinality of continuum, which is, I don't know whether I mentioned that continuum cardinality is that of set of all real numbers. So there are as many Borel sigma fields, Borel sets in RD. So every element of Borel sigma field is called Borel set, and there are as many Borel sets as there are sets in R. There are points in R. Now, at first sight, some people would find that a bit surprising, because you would expect that B of RD is more or less or almost of cardinality of all subsets of RD, but that's not the case. First of all, we should note that B of RD, by definition, is generated by elementary sets, but each elementary set is a disjoint finite union of intervals, d-dimensional intervals. Now, the endpoints or sides of the intervals can correspond to some to any real number, but in fact, just when you think about R, you can every interval AB in R is a countable union of intervals with the endpoints being rational numbers. So there is a sequence AN of rational numbers and Bn of rational numbers, so that An is decreasing and converges to A, and Bn is increasing and converges to B, and in this case we will have that AB itself is the union of these A and Bn. Alright? So basically the intervals generate the entire B of R. But we see that intervals with rational endpoints can generate all these intervals. So actually B of R is generated by all intervals with just with the rational endpoints. And since there are countably many rational points, there are countably many intervals of this kind, and therefore we say that the Borel sigma field B of R is countably generated, or generated by countable collection of sets. And so minimum sigma field containing these rational intervals is again B of R. So now when you think that it's countably generated, then maybe you can step back and say, well, this might not be so unreasonable, that B of R to D is relatively small. It turns out to show this claim, it takes some knowledge of set theory and transfinite deduction on ordinals. Ordinals are cardinals of well-ordered sets. So that's some stuff from set theory. We're not going to do that. We'll just take this as granted. Okay, so that will be all for this first lecture. It's a bathroom lecture because I am in the bathroom. That's the only place where I had some board where I could write. Okay, so end of first bathroom lecture.